This video is about something called titrations. Now, titration is a method by which if you know the concentration of an acid and you react it with a base whose concentration you don't know, you can figure out the concentration of that base and vice versa. Now there's a lot of background here and there's a little bit of math. This is a longer, tougher section in my opinion, okay? And the video will be longer as well to make sure we're clear on that. So there's two basic reactions you need to understand involving acids and base. You should know acids react with certain metals. They don't react with copper, silver, and gold generally, but if you have an acid in general, and this is one way you can identify an acid versus a base. If you throw a metal into it, like let's say you throw some magnesium, it will react and you'll get hydrogen gas and you'll get some sort of ionic compound salt. In this case, you get magnesium chloride. Make sure you know this reaction. It does show up on the regents occasionally, and it's also a good way if they ask you how can you distinguish if an acid or base, throw some magnesium in it. If you see bubbles, it's an acid. It's really easy. The other more important reaction for today is a neutralization reaction. And the products of neutralization reaction are usually pretty similar. So if you have HCl reacting with NaOH, an acid with a base, the H and the OH are going to come together and they are going to make water. The other thing that you're going to get is you're going to get sodium chloride. So you get water, I just misspelled water somehow, and you get salt. And it doesn't have to be table salt, it could be a different one. Now, this is sometimes written in a different way, and I want to show you that because I want you to be clear why that is, okay? Sometimes they draw the ions, like this is the H plus from the HCl, this is the OH from the base, this is the sodium, this is the chlorine. Now you're still going to make water, but as long as the salt is soluble in water, you still have Na pluses when you're done and Cl minuses. They're just floating around the water. And you kind of do this like algebra, right? So like if there's an X on the left and an X on the right, you can cancel them out. Same here. And so a lot of times the neutralization will be written on a regents exam, and you'll just write H plus from the acid plus the OH minus from the base makes water. Because the salt ions are often just still floating in the water, and they really haven't changed. They're called spectator ions because they're not really participating in the reaction. The only thing that's really happening is the H pluses are coming together with OH minuses to make water. Okay? Now, the reactions don't always look exactly the same, you know. So you could have like H2SO4 plus KOH, and you have to write the water out again. And you get a different formula because the K goes with the SO4, and the SO4 is a charge of 2 minus, so you end up with K2SO4. And you should know how I figure that out, okay? And so on and so forth. All right, let's talk about this thing called a titration. Now, as you can see, there's a lot going on this page. All right, so let's first talk about the method. So let's imagine you have, okay, let's a Erlenmeyer flask, which is this type of flask right here, and in it you put 25 milliliters of 0.100 molar HCl. And you've also put phenolphthalein in there. Now let's pause and think about this for a second. Will the phenolphthalein be clear, or will it be pink at that pH? Pause and think if you need to. Well, if you've got an acid in there, right, you'd expect that since the pH color change is between 8 and 9, that below 8, and since there's acid in there, it should be clear or colorless. Now, what you want to understand is what happens as you add base to it. So let's say you have a burette. Now, this is a burette, and we have to remember how we read these things, okay? So we're starting at 1 milliliter here, and what's going to happen is we're going to drip, 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 drip some of this in here. Now, what we're adding here is we're adding sodium hydroxide. So the sodium hydroxide in the burette, and we're dripping it in there, all right? Now, as we drip it in there, a reaction occurs. As it happens, the hydroxides combine with the hydroniums from the acid to make water. And so the amount of hydronium starts to change. The amount of hydroniums gets less and less. And this, remember, the pH scale is kind of confusing. If it becomes less acidic as you add the base, the pH is going to go up, right? And so what you'll see is if you have the pH, if you start, let's say, like a pH of like, you know, I don't know, of like 1 down here, which is what the negative log of 0.1 would be. That's what your original pH would be. As you add base, you're going to see the pH is going to start going up. This would be like volume of NaOH added. Now, as it slowly starts to go up, but then what happens at a certain point, just starts going zoop like this. And it'll get to a point where it goes above 7. Now, why does it go and zoop up like that? Well, it's going to zoop up like that because that's the point at which all of the acid has been neutralized. And at some point, okay, the solution is going to turn basic because there's more base in there than there is acid. At that point, the pH will zoom above 7. And at that point, the phenolphthalein will change from clear and it will turn pink. That doesn't mean that the base is turning pink. The acid turning pink, the indicator turned pink. Now, if you were doing a lab, and I'm going to send you a link from somebody who does a lab, you'll see what this looks like. It's really unfortunate we did not get to do this lab. Who knows? If we come back, maybe we'll do the lab. All right. Anyway, it'll turn pink, and then the curve kind of looks like this. But what's important is this point right here. The point at which it turns pink is where you normally stop. As soon as it starts turning pink, you stop because that means you've neutralized all your acid. And so you now have a volume of base. Now, when you measure the volume of base, you have to be very careful. You start at 1 milliliter, you end at 13.50 milliliters. And what that means is you neutralize 25 milliliters of acid when you use exactly 12.50 milliliters of NaOH. Now, what does this mean? First of all, you need less base to neutralize the acid, which means the base is probably, you think about this, less concentrated, more concentrated. All right? Now, we can now figure out what the concentration of the acid is. Now, watch the math here. I'm going to show you a quick formula, okay? Which then we'll talk about more in the next page. And it's on the back of your reference tables. And basically says if you multiply the molarity of the acid times the volume of the acid, okay, what that will give you, okay, now remember, remember this form of molarity? Molarity equals N over V in liters, okay? If you switch this and you put the V over here, when you multiply them, you will get the number of moles. Okay. Now the only reason why this formula I'm about to give you works is because at the point at which you see this thing going like up like that, that's the point at which the moles of acid equals the moles of base. And so what you get is if you multiply the molarity times the volume, it gives you the moles of H pluses. Now it's actually going to be millimoles if you do it in milliliters, but that's okay, right? Now the thing we know is we also know that that's equal to the moles of hydroxides. And that's only at this one point. That wouldn't be true here, 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 here. But when you get to the point where it turns pink, that's a true fact. Now, the moles of hydroxide are equal to the molarity of the base times the volume of the base. And so what you can do is you can basically take the middle section out, and you get this formula. Molarity of acid times volume of acid equals molarity of base times the volume of base. And then you can plug the numbers in there. As long as you got 3 out of the 4 numbers, you can figure out what the concentration of the unknown is. We don't know the molarity of the base, but we do know the molarity of the acid. And the math can be super easy. For example, here's the molarity of the acid. The molarity is 0.1. I'm not even going to put units in here. 0.1 is my molarity of my acid times my volume of my acid, which is 25, equals the molarity of my base, which is the X I think I don't know, times the volume of base I use. Now be careful. It's how much I use. It's not 1. It's not 13.5, right? It's 12.5. 12.5. Now, I'm going to let you solve for X. So you should pause this and do this. Hopefully you did pause it and do it. Now the answer to this problem is when I solve this thing, I get 0.2. 0.2 molar is the concentration. That is the concentration of the hydroxides. Brackets mean concentration. So basically, this is the formula that you're going to use with some slight modifications. All right, so I've got 2 problems here, okay? And I'm going to talk to you a little bit about the formula and how we have to modify it. So let's do one more of these, okay? Let me just change the numbers here because I think I gave you the exact same problem, and I'm going to change it. Let's say, okay, so let's say we need 40.0 milliliters of NaOH are needed to neutralize 25 milliliters of 0.10 molar HCl. Now, this one's not going to come out as neat, okay, as the last one, but you should still be able to do it. So what do we have? We take the molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base, and we just start plugging numbers in, right? So we have our acid, the molarity of the acid is 0.1, so we put the 0.10 in there again. We've got the volume of the acid, which is 25, okay, equals, okay, the molarity of the base, which is our X again, and we have the volume of the base. In this case, they're saying we have 40.0 milliliters. Now, the milliliters will cancel each other out, so pause it and find the answer. So you should have got an answer of 0.0625 after completing the math. And now what I want to talk to you is a little bit about a a slight variation on the formula, which will show up in maybe one question I give you, but you should be aware of it when you're doing the question. So I've thrown a couple of curveballs in there. All right, and this is how it works. The molarity of the acid really is the molarity of the H plus concentration, which you can see up here, right? So, and the molarity of the base is really the molarity of the OH minus concentration. So the regents sort of throwing a trick in there by not really saying it's molarity of the base, and they usually give you a base with only one hydroxide or an acid with only one ionizable hydrogen. But that's not true always. So I'm going to write an adjustment on the formula. So the formula is going to be this. It's still molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. But on this side, I'm going to put number of OHs. And this time I'm going to put number of H's. And most of the time, the numbers that go in there are going to be 1. But if you look on the left here, there are right in this little corner here, I've given you some examples of acids and bases, okay? So if the base was barium hydroxide, there's very one of these, you end up with 2 hydroxides. Same thing with calcium hydroxide. For every 1 calcium hydroxide, you end up with 2 hydroxides. So in those cases, a number 2 would be placed in here, right? Some of the acids have more than one ionizable hydrogen. For example, sulfuric acid has 2 hydrogen H's out front, and so has 2 ionizable hydrogen. Phosphoric acid has 3 ionizable hydrogens. This one, nitric acid, just has 1, so the problem would stay the same. And carbonic acid would have 2 ionizable hydrogen. Now, everything in the math works out exactly the same except for sticking the numbers in those parentheses if they're not 1s. So let's do this problem really quickly right here. So you have 12.5 milliliters of 2 molar CaOH2. That's the base. So I'm going to put 2 here for the molarity times 12.5 for the volume times the number OH. A calcium hydroxide has 2 hydroxides, so I'm going to put a 2 there. And then on the left-hand side, I've got it says, what is the molarity of the acid? And it gives the volume of 50 milliliters, right? So I'm putting the 50 milliliters here, okay, for the volume. I don't know what the molarity of the acid is, my X. And the number of H's is 1. I mean, I can put the 1 in there, but I don't really need it because 1 times the number itself. And now I can just do the math and solve the problem. So I'm going to pause and do the math. And so the answer is 1 molar. Okay, if you did this correctly, 2 times 12.5 times 2 is 50, and 50 divided by 50 is 1. So the molarity of the concentration of the acid was 1 molar. Now I'm going to do a couple more of these, but I have a 15-minute limit on the video. So what I'm going to do is I'm going to ask you to read them, and then I'm going to show you the setup on these ones, okay? Okay, classic situations is set up a chart like this, all right? The chart seems to make things more difficult, but it really isn't. So they could ask you to figure out what the molarity of the acid and the base is, and they could do several trials or experiments, okay? So you might have to do like subtraction. So if you take the 12.2 and the 14.2, you'll find the volume of NaOH used was 2, and the volume of HI that was used was 5.1. I did that by subtraction, right? Because the difference between those numbers is the actual volume. So this is the volume of base in my first trial, and this is the volume of my acid in my first trial. Then I could do the experiment over again to see if I'm right and average the molarities, right? So in the second trial, I used, I used 2.1 milliliters of the base, right? And I used 5.2, I used 5.4 milliliters of the acid. And I'm giving you that I know the molarity of the base already over here, and so I can plug it in and do 2 problems. So I'm going to pause and draw the setups real quick. So these are my setups, and now I'm going to solve them. Okay, I just did, this is all I had. X is the molarity of my acid in these cases. Now, even though the numbers were slightly different in the 2 examples, when I rounded it for sig figs, which is 2, I got 0.078 molar for both of them. So the average would be 0.078 molar. Now down below, I've got 3 more problems. The only difference is I got different acids, okay, in each of them, and different bases in each of them. So I'm going to ask you I'm going to set up the first one, and then I'm going to show the steps on the other ones and the answers. So in the first one, we get an answer of 6 molar, and that's because the number of H's is 1, and the number of hydroxides is also 1, so that is our result. Now I'm going to do the other ones, taking into account the number of ionizable hydrogens for the acid and number of hydroxides for the bases. So then these ones have some acids and some bases which have different numbers in them. So I'm going to pause it, put in my setups, and then talk about them, and then talk about my answers. And so they're the answers below. And note I've got 2 here because the 2 ionizable hydrogens in the acid. And here I've got 3 on this side and 2 on this side for the number of H pluses in the acid and the number of hydroxides in the base. Thank you. I hope this helps.